This video is to do with basic differentiation techniques of polynomial functions. So differentiation is the start of calculus, and it allows us to find the gradient at a point on a curve, because obviously when we've got a linear function, it's easy to find the gradient of that line because it is a straight line. However, with a curved function, the gradient changes at each point along that curve. So the differentiation techniques that we'll learn today help us find what we call the gradient function, or the instantaneous rate of change at that particular point. So to do this, we need to know a couple of little notations. So we have something that might say f of x, it could say g of x, h of x, any of those sorts of things, and that's the original function. And then if we see one where there is f with an apostrophe, that apostrophe means f prime x. Now f prime x is the derivative, which is what we get when we differentiate a function. And this can also be written as dy over dx, because the d means change in y over the change in x. Because when we're looking at the derivative, we're looking at the rates of change. So we're looking at how x changes and how y changes. So to do polynomial functions, we multiply the power by the coefficient and then decrease the power by 1. That's the general rule. So I've got a few examples to go through, and the first example is y equals 4x cubed. So to get the derivative, which I'm going to write the dy by dx here, we do the power, which is 3, multiplied by the coefficient, which is 4, so that's 12. And then we reduce the power of x by 1. So we end up with 12x squared as our derivative function. So that's a really basic, straightforward one because there's only the one term in the function. Part B, we have two terms in the function, but it's quite simple. We just do each section separately. So we write dy by dx. So we've got y equals 4x squared, take 5x. So again, I'm going to multiply the 2 by the 4 to get 8. Then I'll reduce the power of x by 1. Now that would just be x to the power of 1. And we know that we don't have to write power of 1. Then we move to the 5x. So at the moment, the power of x is 1. So if we do 1 times 5, we get 5. So far we've got 8x take 5. And then when we reduce the power by 1 here, it's going to become x to the power of 0. But if we have x to the power of 0, we know that that just equals 1, so we don't have to write it. The next example is a little bit trickier. It's looking at when there's x's on the bottom of a fraction for a function. And before we even start, what we need to do is we rewrite the function again. So at the moment, we've got y equals 7 over x squared. So we can rewrite that as 7x to the power of negative 2. Because remember, when we have a positive power on the denominator and we move it to the numerator, the power becomes negative. So now when I can do my dy by dx, I'm going to do negative 2 times 7, which is negative 14. And then I'm going to reduce the power by 1, which becomes negative 3. So we've got negative 14x to the power of negative 3, which is also going to be negative 14 over x cubed when it's written with positive powers. So then part B is y equals 5 over x plus 3x squared. So again, we're just going to do y equals 5x to the power of negative 1 plus 3x squared. Now I can do my derivative. So we've got dy by dx. And we do negative 1 times 5 is negative 5. And then we've got x to the power of negative 2 plus 2 times 3 is 6, and if I reduce that power by 1, I get x. So we end up with negative 5 over x squared plus 6x as our derivative for that one. So what we were talking about before is being able to find the gradient at a particular point on a curve. So that's what example 3 is going to be. We need to find the gradient of y equals x cubed, take 3x squared, at the point 2, -4. So if we're ever asked to find the gradient at a point of a curve, that should immediately tell you that we need the gradient function, and the gradient function is the derivative. So the very first step would be to find the derivative. So we do dy by dx equals 3 times the coefficient of 1, so we end up with 3x squared, take 6x as our derivative. Now, if we have this as our gradient function, when we're trying to find the gradient at the point, you'll notice that the y-coordinate that we're given is actually irrelevant because there is no y value in this gradient function. We have dy by dx, and then in our gradient function, we only have x values. So what we do is we sub in just the x coordinate. So we're going to write here, sub in x equals 2. So then we're going to have dy by dx equals 3 lots of 2 squared, take 6 lots of 2. 3 times 2 squared is 12, and 6 times 2 is 12. So the gradient at that point is 0. And then the last example for this video is just looking at an example of real life context where we might have to find the gradient function where it's not just y's and x's or f of x or anything like that. We've got find the gradient function of v equals 4 on 3 pi r cubed. So you might recognize this formula as the volume of a sphere. So what we would need to do here is instead of writing dy on dx, it's not that anymore. It's actually the change in v, so dv over the change in r, so dr. So we've got dv over dr equals. Now what we're going to do is we're going to leave pi as it is because we're going to leave this in standard form. So now we would do 3 times 4 over 3. So if we do 3 times 4 over 3, that just gives us 3, if we write that down, 3 times 4 over 3 times pi, and then we reduce the power by 1. So we end up with 3 times 4 over 3 pi r squared. And then when we do that, we just do 3 times 4 is 12. 12 divided by 3 is 4. So our gradient function for v equals 4 over 3 pi r cubed is 4 pi r squared. So you can just see in the different context, we have to use the letters that are given to us in that context. So hopefully that helps you with basic differentiation techniques of polynomial functions. So it's just important to remember you multiply the power by the coefficient and then reduce the power by 1. And if you have any fractions where the variable is on the bottom, you bring it up to the top, make the power a negative, and then differentiate, and then move powers back to the bottom if they need to be made positive again.